We've seen mercury dataset for a couple of times now, and recall that we've measured mercury content in the sediment of Lake Geneva at different periods. So one period was in 78, another period was in 83. Another one would have been in 88. In 78 and 83, they've used essentially the same locations to measure the content. And we've seen that there is a significant difference between the averages of both years. What I hypothesize now is that there's some sort of a relationship between those two measurements. In the sense that when I had a low value in 78, there was also a lower value than 5 years later. Quite an intuitive assumption, but let's see if we can really formalize that. To do so, we again need the statistical model. Statistical model, part 2. Okay. As data, we have again our mercury content, and let's denote as Xi being the mercury content taken in 1978 at location I. And let's denote as Yi the mercury content taken in 83 at, say, the same location. If there is some sort of relation, we would probably expect a relationship between X and Y, which is maybe something along those lines. And the idea is, well, if I put down some sort of a best fit line, one line that describes the data best, I'm interested in, well, is there a general offset here? This offset would indicate how much overall the level reduced, say, and here the slope. Intercept. What are those values? As model, I propose to use Yi. Okay? We use a statistical model. I like to use capital letters because these are now random variables here. This is, say, intercept beta naught plus slope beta 1 Xi plus some noise or error. Notice here Xi, lowercase, that's fixed. I don't consider that as random. The random part comes in through epsilon I. And here, let me take yellow, intercept beta naught, slope beta 1. I will not go into all the details how to actually get my best values for beta naught and beta 1 given the data here. That is part of a formal statistical course, module, lecture, several lectures possibly. That's deferred to elsewhere. What we'll do in short is we use R to give me the best guess values for those two parameters. These best guess values can then be used again to tackle point 4, statistics to confirm the answer. There is a relationship between the data measured in 78 and 83. Statistical model 2, now here with our RStudio session. So we've shown in a different RStudio session here that there is a significant difference between the levels measured in 78 and 83. And as I've just tried to outline before on the board, we now try to use a linear model to link those two measured data sets. First of all, as usual, I'll open a new script. And let's say here, statistical model part 2, a simple regression using Leman data. Okay, so read in the data, and I would probably put the data in a variable called dot, abbreviation for data or data set, and read comma separated value here of which data set. I would use the one that has both time stamps in it, so 78, 83. I would like to make sure that it's safely loaded. Yes, it is. Okay. As usual, even if I know that the data set is fine by now, a quick sanity check. There it is. Okay. And now I'm going to plot those two variables. Plot that, and I'm going to put on the x-axis the one from the first time point, and on the y-axis the one from the second timestamp. Run. Okay. That looks like that. Okay. Do we see a relationship or not? Well, at least if I squint my eyes, yes, I do see some tendency. Larger values in 78 induce also slightly larger values in 83. Okay. Now, data seems to be okay. Let's use the linear model, i.e. the simple regression model. This is with the command lm, abbreviation for linear model. Now I'm going to use the variable as a response, the one measured in 83. Try to explain that as a function of the one measured in 78. And the linear model should use the data which is within my data set dot. Run. I'll get directly some sort of output, and before I'll go there to explain what it is, well, I should probably put that in some sort of variable. Because in here I have some information, but is that all I really need? So lm out is whatever is contained in it. Okay, so now let's see what lm out is. So print lm out. Well, that's what we've seen before. What is then lm out actually? Lm out is a huge list containing many components. Well, probably not so interesting for us. So I'm going to eliminate this command, and we should use other approaches to access what lm out is. So for example, summary. summary LM out produces as what we see below here. I'm going to slightly increase the bottom console window to have a little bit of better look of what's going on here. This is the summary of LM out. First, we have, say, a recall of the call. How did we produce this LM out variable? Well, it was a linear model where I tried to link these two variables here that are contained in my dot data set. The second part is a short summary about the residuals. The error, the discrepancy between the observations and my fitted line. So median is close to 0. The mean by construction would be 0. The first and the third quartile look about symmetric. Minimum value is very much smaller than the max value. Okay, so we have at least one large residual here, positive large residual. Let's see if we can identify that large residual in a second. Here are the coefficients. A very important table here. The intercept, that was before on the board, beta naught. And the second line corresponds to the slope, beta 1 on the board. The estimates are the estimated value, the best fitted values, best guess of the model with respect to the data. So intercept of 0.18 and the slope of 0.35. The standard error is here quite small, t-values large, hence both of those coefficients seem to be significant. These stars here are just for a quick assessment of what's going on. Residual standard error, these are summaries of the error of the residuals here. Let's look just at the adjusted R squared, 27%. That's not a lot, yes, we agree on that. The F statistic is again significant, so it does make sense to include the variable here. Because we have a simple regression, there is a link between here, this p-value, and this p-value here. Details about all these underlying statistical finesses, that's again part of a classical statistics lecture. So we don't have time to go into all those details here. But this is a very important output, and you should be able to very much summarize what you see there. The coefficients here, those two values, those can be extracted through the command coef, and we can also directly add, say, the fitted line into our plot through upline. I should probably choose a different color here. Col equals, I like blue. And increase the line width to 3. Et voila. Okay. So here we do see the intercept of roughly 0.2, and you do see the slope here of about 0.35. So that means that on average, now let's break here. Okay. Okay. What else can we what else can we extract from the LMOut object? For example, we can extract the residuals. Resit LMOut, and I'm going to put those into a vector called TMP. Our summary TMP, we will get pretty much essentially this line here. And notice again, the mean is 0 by construction. Here we also see this very large value. There was one large value in 83. I'll let it up to you to check where that large value is. Maybe you've seen it already along the array. And that definitely has some influence. And let's see which max of that $HG83 270. So now I'm gonna go back to my script. I should keep everything in here, and I'm gonna just copy this line, Control C, back up here. That's what I need in my script, and as well as this wage max, Control C, Control V. Okay, and then I'll do another linear model. But I'm not copying it up there. I would like to have it down here. And I eliminate this large, huge value. Subset without this value there. I'm going to run it again, and then another summary call. And oh yes, so the max dropped down quite a bit. And notice that by just eliminating this single value, we've increased the R squared quite a bit. I will replot the fitted line, and I'm going to use just a different color. And this is the effect. Okay, so this single value here had as an effect to tilt a little bit this fitted line. So green without, blue with. Okay. What else should we have a look at here? Maybe we should check if we actually do have reason enough to use this linear model. We could, for example, look at some diagnostic plots, and I would just have to insert the variable LMOut into the plot function. And now R produces a series of plots. So this is the first one, where I plot here the fitted values and the residuals, and I shouldn't see too much structure in it, which is about the case here. Maybe the variance slightly increases for larger values. Next plot is a QQ plot, a quantile plot, with an additional to guide the eye line here. And you do see that for the tails, we are deviating a little bit. So here we're too light and here we're too heavy with respect to a theoretical normal distribution. So the residuals are not quite normally distributed, it seems. The next plot is again fitted values on the x-axis and the square root of the standardized residuals, I would like to see again no structure here. There are 3 points that are highlighted. Those are the 3 largest values that maybe would merit some additional examination of what's going on. Residual versus leverage, to see whether there is any additional value that kind of would pull the regression line towards a particular direction. And no, nothing striking here either. So that's okay. Okay, so that's about it for this linear regression setting.